Thank you very much. Let me first say to you once more my pleasure to be here to celebrate the 60th birthday of Theodore Zach, and to recall that he has been such a good advisor for so many of us in doing mathematics. In my case, I call him my young advisor because I have PhD students who are older than him. And I would like also to thank very much Jean Kwak for so well organizing this meeting, this conference, making life so easy for all of us. I've had exchange in mathematics with him for so many years. I think we started 16 years ago or something like that. And then I was away from research for 10 years, so he was nice enough to invite me. He heard that I was going back to research, and he invited me, although there was no reason for that. So I think it's very nice. Okay, thanks a lot. So I would like to talk to you today about something which I call the k-secant lemma. And the reason for that work, I should say before that this is common work with Laurent Grezon, another of my old friends. And for many of the things I'll talk about, Theodore has been really my young advisor, so I can have a lot of help. So the result I had in view all the time is the following theorem. I take the variety, so I use everybody's notation here. They seem to be quite canonical, and they come from Theodore, I think. A smooth variety X of dimension small n in a projective space, and I decide to write n plus c, c being the codimension. Okay? And I want to study a general projection and what I wanted to prove, and I'll explain you why, is the following result, is that if x r in the n plus c minus 1 is the locus, the scheme, let me write the scheme and I have a comment about that, of points of order, maybe I prefer to write xk, of points of multiplicity k larger than or equal to k, then xk is then let me see the drawing. How do I say that? Then codimension, then one codimension xk is equal to k times c minus 1, 2, xk is smooth outside xk plus 1, and 3, the normalization of xk is smooth. So this is the theorem I wanted to prove. It's a theorem, it's true. I think many people think it's well known, probably it's well known, but I never found a proof in the literature I had use for it. So, of course, it's well known in many cases. For example, for what is well known? Let me see. Let me give example. The first and easiest example is c equal n plus 1. Then it is well known that, I think, yes, then it is well known that there are no, it's trivial that there are no, that X is, here I should say that the empty set has all dimension and codimension. Okay? An important remark. Well known that x3 is empty and that x2 is smooth. Well defined. You see here I have written scheme, that is, there is a natural structure. I don't want to go in detail, but there is a natural structure of scheme on xk for each k, and the scheme with this natural structure is smooth outside xk plus 1. So this is a trivial case, and as a first example we have curve in P3 and the famous k-secant lemma, to which I will come back. A little bit more interesting is the Veronese, V, the Veronese surface in P4. Contrary to most people here, I believe the Veronese surface sits naturally in P4. So I insist on that. Each quartic rational curve in P4 defines a unique Veronese surface, and there is nothing more natural in P4 than each quartic rational curve. I'm sorry, each quartic rational curve in P4 defines an associated Veronese surface in P4, so it sits very naturally there. So what happened in this case, if you let me call that Veronese surface S in P4, if you project it to P3, you get the so-called Steiner surface. The Steiner surface is well known. It has 3 double lines. I think Fyodor has talked about it before, and 1 triple point. Okay, and it has something more that I will talk about, but it's another example. It's a good example of why this theorem here, where x3 appears. And as per dimension, you see, here C is 2. Okay, so C minus 1 is 1, and so there is 1 triple point. It has codimension 3 in xk. I should have written codimension xk in that space. It's out this clear, but it's in that space. Okay. So the Veronese surface is an interesting case. I should like to give another nice example. In fact, all Subvarieties are in the same family. If you take, for example, P2 cross P2, which once more sits naturally in P7 and not in P8 for my taste. Okay, and if you project that to P6, okay, then you have a projection, I don't know how to call that, x1. This has, in fact, 3 double plane. x2 consists of 3 planes intersecting in 1 point. That means through 1 point, which is the triple locus, x3. Okay, more interesting perhaps are the Palatini variety, or the variety which Fyodor very nicely called Peskine's variety this morning. Let me write P. Because they are a little bit more interesting. So this is a solid in, let me call that, that's the, how can I, which X is a solid in P5. And in this case, we have a dimension 6 variety in P9. So they have a X2 is, so let me see, in that case, X2 is a surface, smooth outside X3, which is the union of 4 lines. In fact, I should put it this way. X3 is the union of 4 lines through a point, and X4 is the point. Okay, so this is a nice example. And we see what's common with this case. And in the case of the other piece variety, then we have X2 is smooth. Did I say surface? Yes. In that case, it's X2 is smooth. It has dimension 4 and is smooth outside 4 planes through a point. Point is X4. Okay, so those are very nice examples that support this theorem. Now, those examples being more or less explained, I would like to give application of that theorem that were the main reason for which I wanted to begin with to prove that theorem. So I erase the examples. And the first application I had in mind was the following. Let me see, turn it in the right order. The first application I have in mind is a vanishing theorem. And those of you who are familiar with classical geometry and who like to read Castelnuovo know very well that the association between general projection and vanishing theorem is an old tradition in algebraic geometry. And in fact, I think the beginning of many techniques that were used and developed later. So the one I think about is the following. It needs some work, but it's a complex. It can be. This is an important part to prove it. If I have a variety xn in P n plus 2, then we have an H variation in the following way. HL Gx of k is 0 for L plus k plus 1 less than equal to n. You can also write, if you prefer, HL of omega p restricted to x of k equal to 0 for L plus k less than n. It's the same result. So this is one of the applications I had in view. Of course, you should notice that the theorem, in the case n equals 3, you find Fyodor theorem plus Barth h1 over x equal to 0, which is part of Barth's theorem. For the case n equals 4, there is something new. You have the same. You have h1 of gx of 2, so quadratic normality. Okay, and you get something new, which is h1 of ox of 1 equal to 0 plus Barth. So this is not surprising. There's not much new here, but all that can be seen rather easily by the purely algebraic construction as a consequence of this general projection theorem. So that's one type of application I have in view.
You watch your smooth image, right?
Pardon?
You watch your X is smooth.
X is smooth, always. No, you absolutely need that. You use Codera everywhere. Codera's vanishing theorem everywhere to prove this sort of thing. Another type of application I have in view is Subvarieties' famous lemma, which says that if x n is in P n plus c, any dimension, the n plus 2, so I can write sk for the union of k-secant. So this lemma says that Sn plus 2, dimension Sn plus 2 is less than or equal than n plus 1. There is a generalization of this result recently appeared by Eisenberg, recently published by Eisenberg, plus this girl who has a name that I cannot remember. Beheshti. Okay. Which says that can be also deduced from that is, it will be if n divided by s plus 2 is less than or equal to k, then dimension sk is less than or equal than n plus s. Okay? If you take s equal 1, you find the first case, and for a larger s, of course s has to be strictly less than c. So that's another application of this theorem. And as another application, I'd like to give a conjecture which generalizes this theorem in other dimension, other codimension, I should say, which we made with Fyodor on a day where, I don't know, I don't think we drank too much, so I believe it's a reasonable conjecture. Can I put your name here with mine, or you don't want to take any responsibility? You don't want to take
alphabetical order.
Okay, the conjecture goes this way. HL of gx of k should be 0 for L plus c minus 1 k plus 1 less than n. So this is a special, I mean, if you put c equal 2, you get exactly that. But in both cases, you have some extra part of the theorem if you have a connected, you take the sub-maximum non-empty xk. If this is connected, then you get an extra part of the theorem, but Fyodor has talked about that part this morning, proved that by other means, so know that there is nothing much new, but okay, those are typical application of such a general projection result. Now, I'd like to say a few things about this theorem. The first one is, this is very easy to prove. If there was no tangent. Okay? And that's why for the case, very easy, I mean, that's why at least for the case of curves in P3, or for the case where C is n plus 1, this is a result which is easy to prove because the tangents do not go through a general point. Here we project from a general point, so we avoid all tangents in some, when in the case of a space curve, or in the case of a variety of dimension n, but in the case where C is n plus 1. See? So this is very easy to prove, and the proof is the same as the k-secant lemma. Goes this way. Think of the k-secant lemma. So you take a k-secant. So I have to avoid. Whatever I do, I draw an inflection point, always. So where do I do? Okay. So how does, what is the classical proof for the k-secant lemma? Classical proof goes this way. Suppose, take a k-secant, and suppose the family of k-secant is too large. You suppose this k-secant belongs to a family of dimension 2 of k-secant. If you suppose that, you can prove that the tangent in the 3 points, let me call that x, y, z. So TCX intersection TCY is not empty, and the same with the other. Etc. Okay? So this is very easy to prove, assuming that the family of trisecant has too large a dimension. So you prove that. So what you get is what is called stationary secant, that is secants where the two tangents meet. So then you forget that this is a trisecant, you forget that point, and you just look at any of the three bisecants which appear here, and you look at the bisecant with this property, with the property that the two tangents meet, and you see that this is in the ramification of a certain map, which is from a smooth variety to a smooth variety, so the general fiber has no ramification, and then you are done. This is the proof of the trisecant lemma. And in fact, to prove this lemma, this theorem, if you can avoid the tangent line, you can do the same. You will take a k-secant, you assume this k-secant is in too large a family, okay, and you do the same. You prove that any k minus 1 secant that you can extract from that k-secant is ramified in some smooth, in a morphism between two smooth varieties. So this is how you can do it. It's a little bit more difficult in that case, of course. That only proved part of it. In fact, you have to be a little bit careful to note that it is very easy, because here I have assumed that the family was too large. But you don't have to assume that the family is too large. You can only assume that the tangent space to the family is too large. So if you get a family of dimension 1 of trisecant, but which is singular, you prove in this way that a singular family of dimension 1 should disappear because it's in the closure of the ramification of something. See? So this is, when I say it's very easy, maybe it's not that easy, but it's quite simple to organize that to prove this theorem. So the difficulty, the real difficulty, comes from the fact that from from n large enough, you get tangent through the general point. Let me give you an example. We go back to the Veronese and the Steiner surface. So if you project it, so the Veronese in P4, as always, and you project to P3 to the Steiner. So as we have seen before, we have a double locus, which is this way, with a triple point here, and over each of this line, in the Veronese surface, you have a conic. And the center of projection is in the plane of each of these conic. So what that means is that you get, on each of those lines, you get two pinch points, because for each of those lines you have a point which is the image of a line which is tangent to the conic, therefore tangent to the Veronese surface, and cut in another point. So you have 6 pinch points, and it is well known in the case of the Steiner, but I don't think there is any theorem where it's proved generally. It is well known that if you project from the general point, the 6 pinch points are not in the triple point. Okay? And here we see appearing one of the difficulties that one will meet in proving that theorem. Because you have to, in order to organize a proof of that theorem, a good induction, you have to take care of the tangent line, of the line which are tangent to the variety that you project. Of course, for curves or for a variety of dimension n in P2n plus 1, you know that the tangents do not go through a general point, so you have no difficulties. So that, as a consequence of this difficulty, I have to introduce a new scheme, the Hilbert scheme, a special Hilbert scheme, and I erase that. So I introduce this following scheme. So angle. So I want to do it this way. I'm going to work with the incidence. So if you allow me, I prefer this notation. The incidence variety between line and the projective space. Okay. And I introduce the following scheme: O, H, B, K1, KR, very unpleasant, of X in Y cross Y cross Y cross Y R times. Don't be afraid, I'll explain. Each time origin. Okay. So what is this OHB for? So first K1, KR, and let me write K equal K1 plus K2 plus KR. O is for ordered. H is for Hilbert. And B is for Boardman. And you will understand why I want to introduce Boardman here also. So, what is the point in OHB? K1, KR of X is the set of linear subspace, linear subscheme Z in X. Linear by linear, I mean on a line. Can I say that? It's okay? So Z is on a line, so Z, that means Z is in the intersection of X and a line, with R points X1 with an order XR in Z, and multiplicity in Xi of Z is larger than or equal to KI. Okay? Why do I have to introduce that? Let me give you an example. When you take, if you take X5 in P7, okay? If you take X5 in P7, through a general point in P7, you will have a double tangent. Okay, so if you take that, you will always have to consider this thing. And you have to study the double tangent also. They are part of the difficulties. See? So if you want to have a general theorem, you have to, and to be able to organize some kind of proof of that, you have to consider all possibilities where that should occur in a situation where you are working. So I introduced this frightening variety, OH, B, K, K1, KR, in that product. So it exists. It exists because we are considering schemes on the line. So you have no problem with the Hilbert scheme when you consider only subscheme carried by lines. So it exists for in any case. And what you are going to do is to show is the following. So you can, let me see, consider, so I'm now going to consider OHB, K1, KR of X cross L, where L, this is, I mean, I'm not allowed to write that, but we understand that there is, for each point there is a given L, and I'm going to consider the projection to the right given by this. And what I want to prove is that the general fiber of this map is smooth of dimension. So now we have to count. First we have the Grassmannian. Then we have R points. And then we have K, the sum of those conditions. It will be minus KC. Just a minute. N minus 1 plus R. I'm looking at the fiber. N is N plus C, the added dimension. Okay, so the point is to prove the theorem. You look at this family, you look at this scheme, parameterizing those frightening objects. Okay? Over this scheme, you have the obvious projective line. I wrote it this way, but I mean, you understand what I mean. This is a point there consists of an element of that scheme plus a point on the line. And then I project to the projective space. Okay? So here, in the case where all the ki's are 1, I'm studying, very simply, k-secant of the type I've seen before. But now I'm thinking of the possibility of tangent. If each of the ki's are positive, it will be a line which is multi-tangent and which is nowhere transverse. And that can exist through a general point in many cases. So in order to organize a good proof for that theorem, you have to consider all cases. And the theorem is much deeper and much more, contains much more information than this one. Says that you look at this map, and this is the general fiber is smooth of the right dimension. And that has a consequence. That has this consequence. It has many other consequences. I can give you another example of a consequence, an interesting consequence. So a corollary of that would be Mahler's theorem on, I call it on higher powers, maybe allow me to call it this way, which says the following thing. You take, it goes this way, you take x in Pn, x is smooth, you take a point O, and for each k, you define nk O x to be the set of point x such that O, you take a point general point, such that the line OX intersect x, multiplicity in x of OX intersection with x is larger than k. Okay? And Mahler's theorem says that for O general, mk OX is smooth of dimension n. I'm going back to my notation. N minus, so k equal 2, so it will be k minus 1 c. Okay. This is very easy to prove for k equal 2. That's essentially the definition of the tangent bundle. But from k equal 3, you get in serious trouble. And for those of you who were here for my last talk Tuesday, even for hypersurfaces, it's very difficult. Not very difficult, but you have a difficulty. Because if you first choose a point, then you get the second power variety of x, and you cannot move the point anymore to make the second variety smooth. As soon as you get the second, you are lucky enough to get the second variety smooth, you get the definition of the third variety, polar variety. But once more, if to be sure it's smooth, you have to move it. If you move it, you have no control about it. So you have to find a way to prove that. This is proved in a celebrated paper of Mather, which appeared in something like 1917. I never understood the proof. But it appears to be an easy consequence of the theorem in the case k equal k1. There is only 1 point. 1 point, so we are looking at, if you look at the definition, if you have only 1 point, you get exactly the definition of Mather's higher polar variety. So this is smooth. This has been used recently in many papers. For example, Ottaviani has used it in one of his papers with Algebra, if I remember well, and I've seen other application for vanishing theorem. Probably you have used these also. Okay. It produced an interesting vanishing theorem, but not the best. Every time you don't get enough vanishing out of this one. I think the general projection gives more vanishing. So this is another application of this type of result, you see. And so now I want to, out of that, I can sort of try to give you the general projection theorem. So here I've introduced xk, but in xk I can, for k equal k1 plus k2 plus kr, I can introduce xk1, k2, kr, the subvariety of xk, which consists let me describe the general point of that subvariety of xk. So it's a point of multiplicity k, but it will consist of x, of the points x in xk, such that the fiber in x, such that, how do I call the projection? P minus 1 of k contains r points with multiplicity in xi of p minus 1 of k to be larger than or equal to ki. Okay? So we have a stratification of xk by the ramification. Okay? Pardon?
P minus 1. P minus 1 instead of k.
Yeah.
P minus 1. Yes.
P minus...
No,
What's it?
I don't see anything. You have
The
to go.
brackets. You should replace k by x.
P minus 1. Multiplicity in the fiber
Over
X is for the fiber of the x.
in xi.
K. Over x. X, not x. Sorry.
What is the point? K or x?
Voilà.
And above also.
Okay. Multiplicity in xi is larger than or equal to ki.
And then the preceding line.
And what? Something missing more.
No, the same
It's
as
the
the
same
same.
thing.
In the previous line.
Here. Thank you. Now, what does the theorem say? And then I'll give you an idea of the proof. Theorem says that xk1 kr has dimension. Here I gave codimension, so I should give the codimension to be in the same spirit. Codimension x k1 kr is going to be, what did I give here? K times c minus 1. So it's going to be k times c minus 1 plus r. That's the first part of the theorem. So for each time you put together 2 points, the codimension goes up by 1. Okay? And furthermore, x k1 kr is smooth outside here it's ordered, here it's not ordered. Forget about it. If I hadn't said it, nobody would have said anything. So, but you understand what I mean. So is smooth outside x k1 kr 1, okay, which is the intersection of x k1 kr with xk plus 1. So with this stratification, you get the tools to prove the theorem. Now I will give an idea of the proof, a sketch of the proof, and then you will be free to forget completely about the whole story. So, sketch of the proof. And when you see the sketch of the proof, you understand why I had to be, what I have to introduce those varieties and to take an order, the ordered Hilbert scheme. Let me put it here. There is a natural map from O, H, B, K1, KR of X to O, H, B, R. K1, KR minus 1 of X. That's the whole point. What is this map? If KR is equal to 1, here I have 0. The point with multiple 0 is just to forget it. So it will be a forget morphism. If KR is larger than 1, what do we have? We have a point with multiplicity kr on a line. There is only one subscheme with multiplicity kr minus 1 concentrated in that point. So this is a perfectly well-defined morphism. See? And now, once you have understood that morphism, so you see, you prove the theorem which is there. I mean, the proof of the theorem there goes the following way. So I have this goes to Pn, P n plus C. This goes to P n plus C. Here, let me call that this projection P. Here P, because it's the same. And the essential point to prove the theorem is the following. If the point Z in OHB, I take a point, OHB, K1, KR of X is a singular point in that Hilbert scheme. Then, if we go that pi of zy, which is here, is in the ramification of P. Okay? And then you are done by induction, because if you assume that this thing verified the theorem, the ramification doesn't dominate, doesn't meet the general fiber. So you prove this way that the singular locus of this thing, okay, doesn't dominate the general fiber. So this thing, I mean, you put out whatever whatever is singular, and you proceed by induction. This is exactly the proof of the k-secant lemma, but it has to be organized a little more thoroughly. And of course, the difficulty is to treat the case where kr is different from 1. The case where kr is equal to 1, we do it as in the case of the k-secant lemma. There are no difficulties. But when it's different from 1, then you go in real difficulties. It's quite reasonable to treat when x is in a hypersurface. Then what you do when x is in a hypersurface is really, I talked a little bit about that Tuesday, it's calculus, okay? But algebraic geometers do not like to do calculus. So it takes time to force yourself to do the necessary calculus. It takes sometimes months, because we hate to do calculus. I hate to do calculus, but it works. Once you have done it for hypersurface, you realize suddenly that it's enough to do it for a hypersurface, because it's a local question. So you work in the neighborhood of a secant, but in the neighborhood of a secant line to the variety can be defined as a complete intersection. Okay? So you choose a bunch of hypersurface which define locally of the right number of hypersurface which define locally the variety, and you do calculus the right number of times, and you prove that theorem. Okay? So that's the theorem. That's the way to prove that theorem. It proves that, it proves much more, and it may be that it's well known, I mean, at least supposed to be known. I'm not sure. I doubt that there is a complete proof of that, but it's possible. We looked with Gozon very much in the literature. Didn't find anything. Even for surfaces in P4, for example, I'm not sure I saw a clear proof of that theorem with the tangential aspect. That is, that you can, if you have a surface in P4, this says that you can avoid to have a pinch point in a triple point. You can separate triple point and pinch point. So for the case of varieties of high dimension, there are so many cases. As I said, you have a dimension 5 in P7, you have this interesting case of the double tangent, which appear, and they form they have a smooth contact. So you have to look, I think, to give a complete proof, you have to look at all the cases. And maybe I should say one thing more about that, and then you will be free, completely free. So what I want to say is the following, because it's in the spirit of this conference. In the case of Subvarieties varieties, all those are all smooth of the right dimension. So you see here in my theorem, I'm just talking about the part of it which is on line through a general point. But in the case of Subvarieties varieties, you have no problem. You don't have singular locus of any kind. Everything is completely smooth. In the case of the second family of variety that Theodore talked about, same for Palatini and the other which begin with the P variety. You see, I'm so proud to have my variety, thanks to Theodore. So I cannot avoid to speak about it. So it's also true. They're all smooth. Interestingly enough, they are all completely characterized by one mother locus. You see, in fact, the smallest mother locus in each case characterize the Subvarieties variety. You characterize the Subvarieties variety or the Palatini or P variety. So those are very, the variety we introduce here are very interesting because all classical varieties, they act perfectly. They produce no problem. They have no singular locus, nothing. And one of the difficulties when you know nothing about the variety is really to try to understand, for example, you know as well as me, that when you have a curve in P3, you can have a curve of 4-secant, which is completely illegal, but it exists. Okay? You can't have, as we know, thanks to Kaji, tangent meeting the curve everywhere else. So this is something which doesn't appear here because such lines do not go through a general point. So here we are just studying lines through a general point. But I'd like, in the spirit of that, of studying this family, to try to find another proof of your theorem. So those are interesting family in any case. For many other classical varieties, all those schemes are perfectly regular and have a very good behavior. Okay, they are interesting, so I like them, and that's why I wanted to talk about them to you. Thank you very much.